In this session, I will be explaining about coordination compounds. When I say coordination compound, it is the compound based on coordination bond. And this can also be called complex compound, or this topic can be called complex chemistry, coordination chemistry. Most of the D block elements are involved in this coordination compounds. And what do you mean by coordination bond? After all, the coordination compounds have essentially coordination bond. So what do you mean by bond? First of all, a bond essentially requires two electrons, a pair of electrons. Let me consider hydrogen molecule. Hydrogen should have one electron, another hydrogen should have one electron, so they should involve in a bonding. So bonding is nothing but an overlapping of orbitals. It is not the probably that is in your schools or in your textbook they would have shown this as a ball and stick model. But it is not like that, truly speaking. For example, you have got this room and you have got another room. In between that there is a door. So that is the bond, that develops the bond between these two rooms. Do you understand? Let us consider two adjacent rooms. This is one hydrogen room, another hydrogen room. Now we got a door in between that. So the hydrogen cloud, that is the electron, can travel to that room. At the same time, that electron present in that B room can come to the A room. Likewise, it is a common passage, it is a common facility for the electron to travel here and there within the molecule. Do you understand? When I say hydrogen bond means, if it is a covalent, what is the understanding? This hydrogen will give its electron and the other hydrogen will give its electron. So there is a mutual interaction. And they are not going to stick on to one place as we have imagined. It is a common understanding so that this electron can travel. These two electrons can travel mutually. So the bond is nothing but an orbital overlapping where the electrons can be facilitated to travel around the nucleus of both. Are you able to understand this point? Right. So such type of bond, for example, there is a difference between physical bond and chemical bond. What do you mean by physical bond? Let me take a chalk piece. So I got a chalk piece here. Let me break this chalk piece. I got a chalk piece, okay. Now let me break it to pieces. Have I broken the bond, chemical bond? No, this is only a physical bond. It means I have broken the physical forces of attraction among the molecules. So when I have broken a physical bond, that results physical properties like melting point, boiling point, etc. Do you understand? So there is a change of shape as well as size. Otherwise, there is a change of state also during the physical bond breaking. Now we are not going to discuss about this. Let me confine to chemical bond. So I have got a chemical bond and this hydrogen is going to be broken. So it is not a rigid arrangement. Only a rigid body can be broken into pieces. This is very soft, it is only an interaction of electrons. So you have to use this language, cleavage of bond. So when I say cleavage of bond, how it can be cleaved? That is, it can be a homolytic cleavage or heterolytic cleavage. In the case of chlorine, let me consider chlorine. Chlorine has 17 electrons. Another chlorine has 17 electrons. So the outermost electron can interact with these two chlorines. So it means they can, all these 7 electrons occupying in the top, the outermost shell, can travel along this Cl2. That is the arrangement for which an electron can be exchanged here. So this is mutually sharing of electron, one electron, and thereby The ultimate idea of bond formation is to attain the stability of the compound. So octet rule, according to octet rule, each participating element should have 8 configuration, 8 electron system. That is called octet system of electron. So, and that is why we call it octet rule. So the molecules which obey the octet rule definitely will be stable, is it not? So thereby we can classify this type of bond into of course 4 types. One is covalent bond, second is ionic bond, third is metallic bond, fourth is dative bond. So this dative bond can also be called coordination bond. Do you understand? Right. Now let me consider the first one. What do you mean by covalent bond? When I say covalent bond, you must highlight this important term, that is mutual sharing of electrons. For example, both the participating elements are electronegative. Do you understand? So if it is the case, it will be a covalent bond. Electronegativity means what? Electron withdrawing tendency. So both the participating atoms, for instance, in the case of chlorine is electronegative. Another chlorine is also electronegative. So in that case, they have the equal sharing, and that's why we call mutual sharing. Are you able to follow? So there is no difference in the electronegativity as far as the covalent bonds is concerned. So electronegativity plus electronegativity results covalent bond. Do you understand? And electropositivity plus electronegativity results ionic bond. For instance, electropositivity means what? Electron releasing tendency. So electron releasing, one participating element will have the electron releasing tendency, the other one will have the electron withdrawal tendency. So the electron withdrawal tendency is known as technically electronegativity, and this one electropositivity. So usually metals are electropositive, non-metals are electronegative. So when there is a combination of metal and non-metal, definitely you can anticipate the formation of ionic bond. Why? Because metal has the nature of releasing the electron, and that is why this is electropositive. Whereas in the case of chlorine, let me consider sodium chloride. Sodium is electropositive, a metal, it releases electron. What about chlorine? Yes. So thereby it forms an ionic bond. So electropositivity plus electronegativity results what type of bond? Ionic bond. This ionic bond can also be called electrovalent bond. Are you able to follow? Electrovalent bond. Clear? Or it can also be called electrolytic bond. Almost electrolytes are having such type of bonds. What do you mean by electrolyte? It's an acid or base or salt which can conduct electricity in the molten form or in the solution form. Are you able to follow? So this is called electrolyte. So electrolytic compound means, for example, sodium chloride as such will not conduct electricity, but the molten sodium chloride will conduct electricity because of its ionic nature. So the essential condition here is the ionic mobility should be there. So for which there should be some fluidity. So that is possible in the case of what? The molten salt like sodium chloride, or the dissolved salt in water like water or any other polar compound. So that you have got sodium chloride solution. Okay, so this results ionic compound. Ionic bond results ionic compound. Covalent bond results covalent compound. So covalent compounds are generally non-polar, and electrovalent compounds are, electrolytic compounds are ionic compounds. They are polar compounds. So all polar compounds are soluble in polar solvent. All non-polar solutes are soluble in non-polar solvent like benzene, toluene, etc. You got this point? Right. So I think I have explained about the ionic bond, covalent bond. Then let me talk about the metallic bond. What do you mean by metallic bond? Metallic bond is nothing but the combination of two metals. Both the participating elements are electropositive here. Okay. So electropositivity plus electropositivity results what kind of bond? Metallic bond. So briefly, we can easily summarize here. Electronegativity plus electronegativity results covalent bond. Electropositivity plus electronegativity results ionic bond. Electropositivity plus electropositivity results what type of bond? Yes, metallic bond. So we have completed all these three types of bond. Okay, right. Now let us move to the dative bond. So here the pair of electrons are, in this case, that is, two electrons are donated by the donor, the other one will accept. For example, let me consider ammonia. What is ammonia? What is the molecular formula for ammonia? Ammonia, NH3. So NH3, it has a lone pair of electrons. This lone pair of electrons are responsible for the formation of coordinate bond or dative bond. Do you understand this? So let me consider ammonia, which is it has got the pyramidal structure, and at the like a tripod, camera tripod, you know, NH. At the top, like a camera, you have got the pair of electron. That is called lone pair of electron. Why it's called lone pair of electron? It is called non-bonding electron also. So what is the other name for lone pair of electron? Non-bonding electron. So this non-bonding electron, it means it doesn't involve in bonding. But in certain cases, like in the case of coordinate bond, okay, it develops a bond by donating a pair of electron to the incoming element. For example, you have got ammonia, a base, a weak base. Hydrochloric acid is a strong acid. It approaches the weak base. Definitely what will happen here? A lone pair of electron is donated to what? The incoming HCl, in this case hydrogen. And since it has lost its own electron, the ammonia becomes a cation, and that is why we call it ammonium cation. Now it becomes NH4 plus. Do you understand? So this is the very basis idea about the complex compound or coordination compound. Okay. So we have now NH4, and that is a bound within the sphere. And you have got the chlorine also. So this is NH4 plus, and that one is a Cl minus. So it is becoming ammonium chloride. Probably that is in amines also you would have discussed about this, is it not? What is, see, you have got ammonia, NH3 with a pair of electrons. One hydrogen is replaced. What could be the compound? Primary amine or NH2. And another hydrogen is replaced by hydrogen. What is the compound? R2NH, secondary amine. Another hydrogen is replaced, R3N. Still there is a lone pair of electron. Now when you replace another, I mean you cannot replace further because there is no hydrogen here. But when you take any compounds, alkyl halide, another alkyl halide is added, then it becomes what? Tetraalkyl. In that case we call it tetraalkyl ammonium, then halide, and that is why it's called quaternary ammonium salt. So these are all the background I wanted to discuss with you before discussing the coordination compounds. Okay, is it clear now? Now let us plunge into the topic. See, coordination compound. Look at the screen. Coordination compound. Now we should discuss here about the types of salt. What are the three types of salt? Simple salt, double salt, complex salt. Simple salt means you can take common salt, sodium chloride. When you ionize, what will happen? Sodium plus, Na plus, Cl minus are resulted. Right? And what about double salt? For example, ferrous ammonium salt. Ferrous ammonium salt means that is you have got ferrous FeSO4. Okay, FeSO4. You can note down FeSO4, ferrous ammonium salt. FeSO4. And you have got another salt, ammonium sulfate, NH4 twice SO4. So the combination of these two is called double salt. It's also called Morse salt. நீ தப்பாக நினச்சக்கூட மோர் சால்ட்டுனாக்கா மோருக்கு போடுற சால்ட்டு சோடியம் குளோரைடான்னு கேட்காது. இது MOHR நோட் பண்ணிக்கோ. MOHR apostrophe S, Morse salt. இது பேர் என்ன? Morse salt. அது மோரில் போடுற சால்ட் அது வேறு, இது மோர்ஸ் சால்ட், அது காமன் சால்ட் சோடியம் குளோரைட். ஒரு ஜோக்காக சொன்ன அப்போ தான் ஞாபகம் வச்சுப்பேன். அடுத்தது, now when we ionize this compound, what happens here? Fe2 plus and then NH4 plus 2NH4 plus and then 2 sulfate SO4 2 minus is resulted. Let me write neatly here. That is take down FeSO4 ammonium salt and NH4 twice SO4. Okay, so it is going to be ionized as Fe2 plus SO4 2 minus and then again 2 moles of NH4 plus and then SO4 2 minus. Likewise, they are completely separated. But in the case of, so this is the case with the double salt. Double salt. Okay. So what about NaCl? As I already explained, this is a simple salt because simply it gets ionized. Okay. All in aqueous solution only. You can put aqueous, aqueous, aqueous. Everywhere you can put aqueous. Okay. All are aqueous. So it becomes Na plus aqueous and Cl minus. Right? Now let me consider K4 FeCN 6 times. You may ask me, sir, why you put this square brackets? So there is some significance. I will tell you later. So potassium ferrocyanide. It is also called, by IUPAC nomenclature, it's called potassium hexacyanoferrate. I will tell you how to name this compound by IUPAC system. And you cannot expect, for example, 4K plus and Fe and then Cn etc. Fe2 plus and Cn minus 6 minus. You cannot anticipate like this. Okay, this is ruled out. You cannot form such compound, such ions. Instead, it forms 4K plus as a whole a complex ion is obtained. Are you able to follow? Of 4 minus. So this is of complex nature. That is why this compound is known as complex salt. Are you able to follow? Okay, complex salt. And what about this cation? And this is the complex anion. There arises what? The complex chemistry or coordination chemistry. Okay, so I was explaining about these types of salt: simple salt, double salt, and the complex salt. What is the example with which we explain? Simply take sodium chloride. Complete dissociation is possible into simpler ions. What about double salt? That is also possible. And what about the complex ion? You cannot anticipate. It is something different. Okay, so that is why it is called complex ion. Why is it so? Because this ion is more tightly bound with the cyanide ion, and they are bound by coordinate bond, and that is why it's called coordination compound. So do you understand this concept? And there are two types of valency. One valency is easily ionizable, but the other one, which is kept inside the this is called coordination sphere. The square bracket is known as coordination sphere, and this is not ionizable. So this coordination compound involves two types of valency. One is called, take down, one is called ionizable valency, another is non-ionizable valency. Okay, let us move to the next concept. Now I was talking about the ionizable valency and non-ionizable valency. Okay. Right. Now look at this visual. I was explaining about the primary and ionizable and non-ionizable valency, and this is also called primary and secondary valencies. Here you have got a metal, okay, and the valency is indicated here. There are some inner sphere and there is some outer sphere. Okay, this inner sphere is tightly bound here, whereas outer sphere is, let me consider cobalt, and a cobalt has 1 2 3 4 5 6. So this cobalt has NH3 how many times? 1 2 3 4 5 6 times. They are tightly bound within the coordination sphere, and outside the coordination sphere there are ionizable valencies, that is Cl2. Do you understand this? So these are the two types of valencies. Now I have indicated here with some labels A, B, C, D, etc. Okay. Now what about this A? A is the inner sphere. Okay, take down. A is inner sphere. And as you know, what about C? C is the outer sphere. So inner sphere, outer sphere, right? And what about this? The outer sphere is naturally what? Ionizable. Okay, take down. So outer sphere is ionizable. Inner sphere is tightly bound with the coordination bond with the central metal atom. So in a coordination compound, you can identify a central metal atom, and they are usually from D block elements like iron, cobalt, nickel, copper, etc. Okay, right. And these entities, groups of atoms or even ions surrounding the central metal atom. Okay, now let me label it clearly. You have got the central metal atom. Okay, let me consider cobalt. So here ammonia. So how many ammonia are there? 6, is it not? So 6 ammonia are surrounding the central metal atom, and in the outside sphere you have got chlorine. So this is ionizable, and that is why when you dissolve the salt and ionize it, it becomes a chloride ions only. You cannot split this ammonia from the cobalt. Why? It is tightly bound in the inner sphere. Are you able to follow? Got this point? Right. Next. So I was talking about this primary valency and secondary valency, and as I already mentioned that the central metal atom is there. Take down. So this is the central metal atom, CMA, and these are all called ligands. Okay, these are called ligands. And when I put a square bracket like this, it is called a coordination sphere. Coordination sphere. Okay. right? Okay. Now look at this. I think I have already explained about this, but anyway, let me show this visual so that you can understand better. So initially I was explaining about the chemical bond. These are the 4 types of chemical bond: covalent bond, ionic bond, coordinate bond, metallic bond. Okay. So here we have the donor acceptor bond, which is nothing but coordinate bond. Okay, right. And let me go through the next one. And that is, I already explained about the electropositivity. So you have got sodium. When one electron is removed from sodium, it becomes what? Na plus. And this tendency is called what? Electropositivity. Okay, electropositivity. And electron dash tendency. What is that tendency? Releasing tendency, is it not? And it has got the dash behavior. What is that behavior? Metallic behavior. Okay, right. And what about electronegativity? En, it is represented that is as an abbreviation En. Now you have electron dash tendency. What is that tendency? Withdrawal tendency. So chlorine withdraws electron, accept one electron to become what? Cl minus. Okay, so this is electronegativity. Okay, right. Now Werner's postulates, take down. Werner, he proposed certain postulates as far as coordination compounds are concerned. He talked about the types of valencies. Okay, so I was already explaining about the primary valency and the secondary valency. And there is a primary valency in the central metal atom, and there are types of ions which satisfies the secondary valency also, so that we had to decide whether it is ionizable or not. And we were discussing about 2 types of spheres. What are those? Inner sphere and outer sphere. Okay, now let us explain in detail about the Werner's postulates. So Werner postulates, he said there are 2 types of valencies. Okay, and the valency of CMA is very important. What is CMA? Central metal atom. Okay, and the secondary valency of central metal atom, it can be negative or positive ions, and they are surrounding the central metal atom, and that is why they are called ligands. So what are ligands? It is the ions or atoms or neutral atoms or group of atoms surrounding the central metal atom. So they are called ligands. For example, let me write K4 efficiency once again. K4 FeCN 6 times. Okay, what is the ligand here? Cyanide is the ligand. What is the central metal atom? Iron is the central metal atom. Okay, and outside the coordination sphere you have potassium. So what type of complex ion it is? This is plus, K is plus, so it should be minus. So you can put X for this to find out the valency. You know already plus 1. So in that case 4 into plus 1 plus X is equal to 0. So X is equal to minus 4. So in that case the ion nature is minus 4. And after that you can work out the oxidation state of the central metal atom also. Like Fe, you have Cn, then 6 times, and the result is minus 4, is it not? So you can work out, put X for this. We already know for cyanide it is minus 1. Okay, so X plus 6 of minus 1 is equal to minus 4. So X minus 6 is equal to minus 4. X is equal to plus 2. So it means this is what? The oxidation state of central metal atom is plus 2. So how you are supposed to indicate? You can put this by Roman letter. Do you understand this? Now let us try to give the nomenclature for this compound. For example, in the case of normal IUPAC nomenclature of common compounds, inorganic compounds like sodium chloride, so always a cation should be named first, followed by anion, right? You cannot call chlorosodium, okay? But when you coin the complex name by IUPAC, within the coordination sphere, the ligands should be named first, followed by the metal. Are you able to follow? For example, you have FeCN. What do you mean by FeCN? FeCN twice. What is this? Ferrous cyanide. FeCN 3 times ferric cyanide. Are you able to follow? This is ferrous. So nowadays it's called iron 2 cyanide. Okay, similarly iron 3 cyanide, this one, right? Now listen to me carefully. In this case, when you name the compound, so we have to follow the same IUPAC system, that is always start with the cation. So which is the cation here? Potassium is the cation. So you must call this potassium, and then you have to name this compound, the coordination sphere. Within the coordination sphere, you have to name the ligand first, followed by the cation. Do you understand this? So in that case, this is cyanide. In those days they used to call cyano. Okay. Nowadays they are called cyanido. But both are same. But the latest nomenclature is cyanido. So here, how many atoms are there? How many ligands are there? 6. So 6 means hexa cyano, and this iron, is it not? That should be called as ferrate with its original name. Okay, and because you know very well, all the anions should be concluded with ate suffix. Note this point. All anions particularly, when the complex ion is anion, it should be having the suffix ate. For example, nickel is a compound, okay, it is available as complex ion. In that case, how to call it? Nickel becomes nicolate. Are you able to follow? Right? And what about iron? So iron should be called, it cannot be called ionate. No, the original Latin name should be reflected and add the suffix. So what is the original name for this element name? Ferrum, ate, ferrate. Are you able to follow? So this should be called ferrate. Do you understand this? Ferrate. Now shall we try? Potassium hexacyanido ferrate. What is that? Potassium. Write down potassium. And when you write the nomenclature, you should write it continuously without any gap. Okay. So in that case, you can write like this: potassium. Start with small letter. Potassium. Don't leave any space. Hexa cyanido. Okay. And then ferrate. Ferrate. And bring the oxidation state here. That is 2. Are you able to follow? Got it? So what is the nomenclature of this compound? In those days they used to say cyano only. Nowadays they are insisting on ID because cyanide. So cyanide becomes cyanido. Chloride becomes chlorido. Take down. Cyanide. Cyanide. What you are supposed to do? Strike out E and add O. Cyanido. That's all. Okay. Chloride. So what you are supposed to do? Strike out E, drop E and add O. Chlorido, bromido, iodo. Got it? If you have got carbonate, carbonato. If you have got water, aqua. If you have got, that is any sulfate, sulfato. Okay? Nitro, nitrito, nitrate becomes nitrito, nitrato. Likewise, you should have the suffix O here, right? So in that case, I think now it's pretty clear. That is potassium hexa cyanido ferrate 2 is the What? IUPAC name of this compound. I'll give you one more. You put K3FeCN6. Try this.